You've seen it happen. You deploy an agent for a mission-critical task, and it hits a minor snag, maybe a slightly changed API response or a flaky database connection. Instead of adapting, a static agent gets trapped in what I call the static prompt loop. It repeats the same incorrect logic over and over, burning through thousands of tokens and inflating your compute costs while delivering zero value. In a production environment, this is a death sentence. Most agents today are essentially hard-coded scripts wrapped in an LLM, lacking any mechanism to recognize their own failure patterns or evolve their strategy. We call this the static agent wall, where complexity outpaces the initial system instructions. This failure isn't just about bad prompting. It's a fundamental architectural flaw that ignores the dynamic nature of real-world environments. But wait, is there a way to break this cycle without human intervention? I will show you how the end of static agents is actually the beginning of something far more powerful. Contrast that failure with the Hermes philosophy. When a Hermes-based agent encounters an error, it doesn't just retry the same prompt. It triggers a reflection mechanism that analyzes the stack trace and the environmental feedback. It asks, why did my fetch data skill fail? If the answer is an outdated schema, the agent enters an autonomous evolution phase, retrieves documentation, synthesizes a new skill code, and registers it into its own tool belt all without you touching a single line of Python. This isn't just a clever prompt. It's a self-correcting neural symbolic loop. By the end of this lecture, you'll understand that the value isn't in the model itself, but in the agent's ability to admit it's wrong and fix its own code. But how do we bridge the gap from a simple chatbot to an evolving brain? The answer lies in a complete architectural shift that experts rarely discuss openly. We are moving away from manual prompting and toward building a skill registry system. In this lecture, I will show you how to transform your local LLM from a passive responder into an active architect. We'll leverage the Noose Research Hermes 3 and Qwen 2.5 series to build a multi-layered memory system. This architecture ensures that once a skill is learned, like handling a specific SQL dialect or a niche API, it is persisted and indexed. No more bloated system prompts that eat up your context window. Instead, we use a dynamic loading mechanism where the agent fetches only the code snippets it needs for the current objective. This represents a massive shift in how we think about MLOps for agents. You're not just building a product, you're building an entity that grows more capable every hour it's running. Are you ready to stop being a prompt engineer and start being an agent architect? Let's break down the 4-step workflow that makes this possible. Before we dive into the code, let's look at our technical roadmap. We aren't going to rely on expensive, closed-source APIs. Instead, we'll utilize the power of local LLMs like Qwen 2.5 Coder and the Hermes fine-tuned Serve Ollama and VLM. We'll master the orchestrator layer that sits between the user and the model, managing the iterative improvement loops. By the end of this guide, you will have a blueprint for a system that can autonomously crawl documentation, write its own tool functions, and manage its own long-term memory via vector databases and local JSON stores. This is the stack that separates the hobbyists from the elite AI engineers. Now, we have our requirements and our vision clear. But this begs the question, what does the brain of such an agent actually look like on the inside? In the next chapter, we dive deep into the anatomy of a self-improving neural structure. In the world of local LLMs, most developers treat the model as a single monolith, which is the first step toward a scaling disaster. When you look under the hood of a high-performance Hermes-based agent, you don't see one giant brain trying to do everything. Instead, you see a sophisticated orchestrator sub-agent architecture. The orchestrator acts as the high-level reasoning engine often powered by Hermes 2 Pro Qwen 2.5, which doesn't execute tasks directly but manages a fleet of specialized worker agents. These sub-agents are spawned dynamically to handle specific domains like file I/O, web scraping, or code synthesis. In a local environment, this means we can manage context windows more effectively by isolating task-specific data within the sub-agent's memory, preventing the lost-in-the-middle phenomenon that plagues large, singular prompts. This isn't just theory. It's how we achieve low-latency responses on consumer-grade GPUs like the RTX 4090. But wait, how does the orchestrator actually decide who does what without hallucinating a mess? The secret to the Hermes brain isn't just raw parameters, it's the recursive task decomposition process. When a complex goal like build a full-stack weather app and deploy it locally hits the system, the model doesn't just start typing. It utilizes a structured reasoning loop where the objective is shattered into atomic, executable subtasks. This is where the self-improving aspect begins to germinate. Each subtask is assigned a priority and a dependency map. If a subtask fails, the system doesn't just throw an error. It reevaluates the parent goal and modifies the decomposition strategy in real time. In my experience, this is where most toy agents fail. They lack the recursive error correction logic that Hermes experts bake into the system prompts. By treating every failure as a data point for the next decomposition cycle, the agent literally learns the boundaries of its environment. But this decomposition isn't happening in a vacuum. It needs to touch the real hardware. How do we bridge the gap between abstract reasoning and actual mouse clicks? To make an agent truly autonomous, we have to move beyond text in a box. This is where the interaction between the core Hermes logic and peripheral interfaces like computer use and WebUI comes into play. We use a standardized interface layer that translates the agent's high-level intents in specific API calls or GUI interactions. For instance, when Hermes needs to verify a local deployment, it doesn't just guess. It triggers a headless browser agent via a WebUI interface to check the DOM for specific elements. This requires a tight coupling between the reasoning engine and the tool calling schema. In the local LLM stack, we often use a middleware like Ollama or VLLM to serve the model, while a separate Python backend manages the browser automation. The beauty of the Hermes fine-tune is that it's specifically optimized for this JSON-based tool interaction, reducing the syntax errors that usually kill automation scripts. But if this sounds like what OpenClaw or other agents do, you're missing the critical scaling factor. Let's compare the two directly. When people ask why I prefer the Hermes architecture over something like OpenClaw, it comes down to multitasking, resilience, and resource management. OpenClaw often struggles when the sub-agent count exceeds 3, as its central controller gets bogged down by context overflow. Hermes, however, utilizes a more efficient attention mechanism and specialized system prompts that prioritize state tracking. While OpenClaw is fantastic for single-threaded tasks, the Hermes Qwen ecosystem allows for inter-agent communication, where sub-agents can share insights without flooding the orchestrator with every line of logs. This horizontal scaling means you can have one sub-agent debugging code, while another is concurrently scraping documentation for the fix. In real-world local deployments, this efficiency translates to a 42% reduction in token usage for the same complex goal. Now, you might be thinking, this is great, but the agent is still limited by what it was trained on. That's where we move from static brains to dynamic skill generation. How does the agent learn a new trick on the fly? Let's get into the engine room. The most groundbreaking feature of modern Hermes agents is the transition from fixed prompts to dynamic skill generation using Group Relative Policy Optimization, or GRPO. Unlike traditional PPO, which requires a complex value model that eats up VRAM, GRPO optimizes based on group performance metrics. This makes it perfect for local LLM setups. The agent doesn't just guess a new skill. It generates a group of potential candidates, tests them, and uses the relative success of those candidates to update its internal policy. This is reinforcement learning in its most practical form for local environments. It allows the agent to refine how it writes Python scripts or how it queries a database without you ever having to update the underlying model weights. It's essentially training itself on the fly within the constraints of your hardware. But how does the machine actually know if it's doing a good job or just creating digital garbage? The feedback loop is where the magic happens. Every time a sub-agent executes a code block or performs a web search, the output is passed through a reward model. In a local Hermes setup, this reward model is often a lightweight version of the agent itself or a set of hard-coded heuristics like did the code run without errors, or is the JSON valid? If a subtask succeeds, that specific behavioral pattern is reinforced in the agent's episodic memory. If it fails, the system triggers a backpropagation like logic not into the model's weights, but into its system strategy buffer. This is how the agent learns that using a specific library for a task is better than another. It's the difference between an agent that repeats the same mistake and one that says, I tried that library, it failed 3 times, I'm switching tactics. But for this to be permanent, the agent needs a place to use the learned skills. Is it just writing temporary scripts, or is it building a library? Persistent skill generation is the save game feature of AI. Instead of rewriting the same scraping script every time, the Hermes agent generates a reusable JSON-wrapped tool. Look at this code snippet. The agent doesn't just write a script, it creates a structured tool definition including the name, description, and required parameters. Once the reward model validates this tool, it's saved into a skill library, a local database, usually SQLite or a simple JSON file, that the orchestrator queries at the start of every session. This means your agent actually gets smarter and more capable the more you use it. It's building its own custom toolbox tailored specifically to your workflow. This is a massive shift from the stateless nature of ChatGPT. Here, the agent owns its tools. But we need to be careful how much compute are we burning on this self-improvement, and is it worth the cost compared to just writing the code ourselves? Finally, let's look at the efficiency reality check. Manual coding is great for precision, but it lacks the scale of autonomous generation. In a typical development cycle, creating a set of 10 specialized tools for a project might take a human dev 5 to 8 hours. A self-improving Hermes agent can generate, test, and refine those same 10 tools in about 15 minutes of compute time. While the accuracy might start lower, the GRPO feedback loop ensures it reaches parity with human code within a few iterations. The cost: pennies in electricity for your local GPU versus hundreds of dollars in developer time. This is the ROI that Hermes experts keep secret. They aren't just using AI to code, they are using AI to build the systems that code. But all this knowledge, the skills, the logs, the failures will disappear if the agent doesn't have a way to remember them across sessions. That brings us to the most complex part of the brain, hierarchical memory. Ready to see how we store a lifetime of skills? In the world of autonomous agents, a massive context window is often treated as a silver bullet, but in practice, it is a recipe for hallucinations and high latency. Experienced developers know that a truly self-improving Hermes agent requires a structured approach to cognition, much like the human brain. We categorize this into 3 distinct layers. Short-term memory handles the immediate now, the current conversation turn. Long-term memory acts as the expansive library of facts and generalized skills. Crucially, episodic memory captures the story of specific tasks, what worked, what failed, and the specific sequence of actions taken. Without this hierarchy, your local LLM will struggle to distinguish between a temporary variable and a core architectural pattern. It is not about how much the agent remembers, but how it categorizes that information for future retrieval. This structure ensures that the model stays grounded in reality while maintaining a high-level strategic overview of its goals. But how does a machine differentiate between a fleeting detail and a core lesson worth keeping? Question: this distinction is handled by our semantic retrieval layer, which we will examine next. To implement long-term memory in a local environment, we rely on vector storage and semantic search rather than simple keyword matching. When a Hermes agent performs a task, it doesn't just store text, it converts that text into high-dimensional vectors using models like BGEM3 or Qwen-based embeddings. In a local stack, tools like ChromaDB or Qwen allow the agent to perform semantic retrieval, finding information based on meaning rather than exact words. If you ask the agent about a database connection issue it solved last week, it uses vector similarity to pull relevant episodes even if the phrasing is different. The real engineering challenge is the embedding latency. On a local workstation, you must optimize the vector dimensions to ensure that the search doesn't block the LLM's reasoning process. This is the difference between an agent that guesses and an agent that knows based on its own historical data. Retrieval is easy, but keeping that retrieved data relevant is where most local agents fail. Payoff: I will show you the distillation trick next that prevents your vector DB from becoming a swamp of useless data. If an agent remembers everything, it effectively understands nothing. This is where memory distillation comes in, inspired by the psychological concept of the forgetting curve. In the Hermes framework, we implement a background process where the agent reviews its own episodic logs to identify recurring patterns. Instead of keeping 10 logs of fixed a Docker permission error, the agent distills these into a single high-confidence knowledge node. This node contains the generalized solution and the why behind it. This prevents the context window from being flooded with redundant information. It's a process of lossy compression where only the signal remains and the noise is discarded. When you observe your agent getting faster and more accurate over time, you are seeing distillation in action. This is the secret sauce for self-improvement. The agent is literally writing its own textbook based on its life experiences. Theoretical memory is one thing, but where do you actually store this on your local workstation without crashing your system? Teaser: in the next section, we tackle the physical implementation using local databases. When moving from theory to local hardware, the choice of database is critical. For most local Hermes setups, I recommend a dual database approach. Use SQLite for your structured metadata and agent state tracking because of its zero-config nature and extreme reliability. For the actual vector embeddings, a local instance of PostgreSQL with the vector extension is the gold standard for those who need scalability, though ChromaDB is excellent for quick prototyping. The main bottleneck we see in the field isn't storage capacity, it's I/O latency. If your LLM has to wait 500 neos for memory retrieval every time it thinks, the agent will feel sluggish. We optimize this by keeping the most frequently accessed skill nodes in a local cache or a simple JSON buffer. This ensures that the agent's instincts are available instantly, while its deep memories are fetched only when needed. Once the database is ready, the real challenge is context window management. Question: how do we fit a month of history into a limited 8K or 32K window without losing the plot? Let's walk through a real-world scenario. Imagine your agent encountered a specific Python library dependency conflict 3 weeks ago. Today, you give it a similar deployment task. In a naive system, the agent would make the same mistake again. But with hierarchical memory, the agent initiates a contextual recall. It searches its episodic memory for dependency conflict, finds the distilled skill node it created previously, and injects that specific fix directly into its current prompt. This happens even if the current project has a different name or structure. We manage the context window by using a sliding window for conversation history, while reserving a fixed slot for these retrieved skills. This way, the agent doesn't need to relearn. It simply remembers the solution. This is how you achieve infinite functional context on local hardware with limited RAM. So we've built the storage and retrieval, but what's the final verdict on why this hierarchy beats a simple RAG setup? Payoff: the answer lies in the agent's ability to actually evolve its own logic. To wrap up, hierarchical memory is what transforms a standard chatbot into a high-performance self-improving agent. By separating short-term context from distilled long-term skills, we solve the two biggest problems in local LLM deployment: context window saturation and the repetition of past mistakes. This structure is the key differentiator for the Hermes ecosystem. While others are waiting for models with million-token windows, we are building agents that use intelligence to manage their own knowledge efficiently. We've looked at the architecture and the persistence. Now it's time to get our hands dirty. Memory is the brain's library, but a library is useless if you can't act on it. Teaser: in the next chapter, we move from architecture to implementation, running Hermes on your local machine and setting up these memory layers in code. In the field, we often see teams burning thousands of dollars on cloud inference before realizing that local deployment is not just a cost saver, but a privacy requirement. To get Hermes running, we start with Ollama. Qwen 2.5 or the latest 3 series variants are our preferred engines because they handle the Hermes prompt format with high fidelity. You aren't just pulling a model, you are configuring a reasoning engine. Look at the model file. We must explicitly set the temperature and stop tokens to prevent the model from hallucinating during the self-improvement phase. Most developers fail here because they use default settings, causing the agent to loop indefinitely. By customizing the system prompt within the model file, we anchor the Hermes orchestrator's behavior right at the inference layer. This ensures that every token generated follows the strict JSON schema required for tool calls. But just running the model isn't enough. You need to know if your hardware can actually handle the heavy reasoning load required for recursive self-improvement. Question: is your current GPU actually capable of running this without errors? Let's check the benchmarks. Experienced developers know that TLOPs are a vanity metric. Memory bandwidth is the real king when running local agents. If you're on a macOS M series, you're leveraging unified memory, which is fantastic for large context windows, but NVIDIA users still hold the crown for raw throughput in parallel sub-agent processing. In this table, we compare the Q4KM quantization, which is the sweet spot for local SELP setups against FP16. Notice how the token per second rate drops significantly once you hit the 32K context limit on consumer hardware. When running the Hermes self-improvement loop, the agent needs to think through its previous failures, which balloons the context. If you're running on an RTX 4090, you'll see great speed, but memory will be your bottleneck. On the other hand, Mac Studio users can fit larger models but at a slower generation speed. Payoff hardware is set, but how do we bridge the gap in the raw engine and our agent's brain? Next, we'll map the connection flow. Now that the server is up, we must connect the Hermes WebUI or your custom Python orchestrator to the local Ollama instance. This is where most junior devs get stuck on connection refused errors. You need to ensure the Ollama host is bound to 0.21 error if you're running in Docker, and the core's origins are explicitly allowed. The connection flow starts with a heartbeat check, followed by the model capability discovery. We point our API base URL to localhost 1434 v1, mimicking the OpenAI API structure. This abstraction is vital because it allows you to swap a local Qwen model for a cloud-based GPT-4 for debugging purposes without changing a single line of logic code. It's the plug-and-play architecture that makes Hermes so resilient. Teaser connectivity is only half the battle. The real magic happens when the agent starts talking to the outside world using a standardized protocol. If an agent can't touch the real world, it's just a chatbot. This is where the Model Context Protocol, or MCP, comes in. Developed to standardize how LLMs interact with external data, MCP acts as the USB port for your Hermes agent. Instead of writing custom brittle integration code for Slack, GitHub, or your local file system, use an MCP server as an intermediary. The architecture consists of the host, which is our Hermes orchestrator, and various clients that communicate over JSON RPC. This separation of concerns means your agent doesn't need to know how to call a GitHub API, it just needs to know the tool definition provided by the MCP server. It's a game changer for local LLMs because it offloads the complexity of authentication and rate limiting to a dedicated layer. Question theory is fine, but let's look at exactly how a message turns into an automated action across multiple tools. Let's trace a real-world data flow. A user sends a message via Telegram, "Hey Hermes, summarize my last 5 GitHub PRs and post it to the dev Slack channel." The Hermes orchestrator receives this and identifies 2 distinct skills needed. It doesn't do this sequentially. It spawns parallel sub-agents via the MCP server. One agent fetches the PR data while the other prepares the Slack formatting. The data flows from the Telegram webhook into the orchestrator, which acts as a traffic controller. It parses the JSON response from the GitHub MCP server, passes it through a summarization skill, and then pipes that output to the Slack MCP server. This piping mechanism is what we call skill chaining. It's powerful, but it's also where the most common failures occur, usually due to mismatched data schemas between tools. Teaser: everything looks perfect on paper, but if you miss one environment variable, the whole system collapses into a connection refused loop. Before you hit deploy, you need a cold, hard look at your environment configuration. I've seen countless production-ready agents fail because of a missing API key or a misconfigured port that only worked on the developer's machine. This checklist is your survival guide. First, validate your MCP server endpoints. Can the orchestrator actually reach them? Second, check your memory allocation. If you haven't set a hard limit on the context window, your local LLM will crash your entire system when it tries to ingest a massive log file. Third, ensure your self-improvement flag is toggled on only after you've verified the basic skill chain. Running an unmonitored self-improvement loop on a local machine is a recipe for a thermal shutdown or a disk-filling log explosion. Payoff: with the local setup complete, the next step is surviving the chaos of a real production environment, which is exactly what we'll cover in our Battle Stories chapter. In theory, a self-improving Hermes agent sounds like a dream, but in production, it often looks like a nightmare of redundant scripts. I've seen systems where the agent, attempting to fix a minor file parsing error, generated 5 different versions of the same tool, naming them Search V1 through Search Final V2. This skill bloat doesn't just waste disk space. It confuses the model's tool selection logic, leading to a hallucination loop where the agent calls a broken tool to fix the very tool it just broke. You start seeing the model apologize to itself in the logs. To prevent this skill rot, you must implement a strict validation layer that run unit tests on any new code before it's promoted to the permanent skill library. If the test fails, the skill is discarded immediately. This keeps the workspace clean and the logic sharp. But wait until you see what happens to your VRAM when these agents start calling themselves recursively in an attempt to solve these errors. Local LLM deployment is a game of resource management, and recursive agent calls are the fastest way to hit an out-of-memory error. When your Hermes orchestrator decides to spawn 3 subagents to handle parallel tasks, it's not just doubling the compute, it's multiplying the KV cache requirements. On a local RTX 4090 or even an A6000, you'll see your VRAM vanish in seconds if you don't cap the recursion depth. I've seen production pipelines crash because an agent entered an infinite loop of asking for clarification from a sub-agent that was also waiting for clarification. You need to implement a global token budget and a hard limit on sub-agent spawning. Always monitor your context window usage if the agent starts forgetting the initial goal, because the skill generation logs are too long, the whole system collapses. If you think managing RAM is hard, wait until you realize that a fully autonomous agent is essentially a security vulnerability waiting to happen. The biggest mistake beginners make is striving for 100% autonomy. In the real world, fully autonomous mode is a risk most businesses can't afford. You need human-in-the-loop or HTL gates. Think of it as a checkpoint where the agent says, I've generated this bash script to optimize your database. Should I run it? Without this, one hallucinated RF command can end your day. We use a confidence score threshold. If the Hermes model is less than 90% confident in its tool selection, it must pause and wait for a human signal. This doesn't slow down the agent as much as you'd think. It actually prevents hours of rollback work caused by autonomous mistakes. Effective HTL is about managing state. The agent should be able to resume exactly where it left off once the human gives the green light. The logic of these gates depends entirely on one thing, the quality of the prompt that dictates the hierarchy. Let's talk about the golden prompt. For Hermes 3 or Qwen-based agents, the system prompt is your source code. If your prompt is vague, the model will output conversational filler instead of structured JSON. You must use clear XML tags to separate thinking from acting. This prevents logic circularity, where the model starts talking about what it should do instead of actually doing it. I always include a strictness clause. You are a function calling engine. Do not explain your actions unless the task fails. We also use meta-prompting, where the agent has a specific section in its memory for lessons learned from previous failures. This prompt structure ensures the orchestrator stays in its lane and doesn't hallucinate that it's a chatbot. Even with a perfect prompt, if your agent has access to your shell, you're one hallucination away from a deleted root directory. Security is the final, non-negotiable step. If you're using the computer use feature where Hermes can execute shell commands or move the mouse, you must sandbox it. Never run an agent with root privileges on your host OS. We use Docker containers with restricted network access and mounted volumes that only contain necessary data. I also recommend using tools like gvisor to provide an extra layer of kernel isolation. This checklist is your shield. If an agent tries to reach out to an external IP it shouldn't, your firewall should be the one to kill the process, not the agent's own ethics. Remember, an agent is just a statistical model. It doesn't know right from wrong, it only knows the next token. Now that we've secured the trenches, it's time to look at the horizon, the ultimate path to true agentic autonomy in our final chapter. We have covered significant ground in this journey. In the real world, building a self-improving Hermes agent isn't about magic. It's about the technical interplay between structured hierarchical memory and the GRPO-based skill generation loop. Most beginners fail by dumping everything into a flat vector database, but experienced developers know that separating ephemeral task state from persistent skill primitives is what keeps the agent from drifting into incoherence. We looked at how Hermes 3 leverages group relative policy optimization to evaluate multiple skill candidates simultaneously without needing a heavy reward model. This architectural choice is the difference between an agent that forgets its purpose and one that evolves its own toolset over thousands of iterations. Understanding the distinction between the system prompt and the dynamic skill library is your first step toward true mastery. But having the architecture is only half the battle. How does this internal architecture translate into the broader industry shift we're seeing right now? Let's look at the horizon. The industry is rapidly moving past simple chat interfaces. We are entering the era of the autonomous AI employee. In the past, LLMs were just calculators for words. Now, with the self-improvement loops we've discussed, they are becoming systems that manage their own life cycle. We're seeing a massive shift where local execution via tools like Ollama and specialized fine-tunes like the Hermes series will outperform generic cloud APIs for specialized agentic workflows. Why? Because latency and data sovereignty are the ultimate bottlenecks for true autonomy. If an agent has to wait 3 seconds for a cloud response just to decide its next self-correction step, the self-improving loop breaks. The path to AGI isn't just one giant model in a data center. It's millions of small, self-improving agents working in concert across local infrastructure. This, the paradigm shift you are now prepared to lead. But wait, knowing the future is useless if you don't have the tools to build it today. It's time to move from the passenger seat to the cockpit. Your immediate priority is to clone the reference implementation we've analyzed and set up your local environment. Don't start with a massive GPU cluster. Use Ollama to serve a quantized Hermes 3 Llama 3.18b model on your local machine to understand the fundamentals. Experiment with the memory sync script first and observe how the agent logs its own failures and generates a skill patch to fix it. This feedback loop is the heartbeat of agentic autonomy. If you don't experience the aha moment when a local model corrects its own Python script error without human intervention, you're missing the core of this revolution. Start small, run the loop, break the code, and analyze the logs. Real expertise isn't built by reading docs, but by debugging the edge cases of an autonomous loop. Once you've got the loop running, you'll realize you're part of a much larger movement. Building in isolation is the fastest way to hit a wall. Engage with the NAS research community and the growing ecosystem of local LLM developers. The secret that experts won't tell you isn't a hidden line of code. It's the persistence to refine the reinforcement loop through thousands of iterations. As we conclude this journey, remember that the most powerful AI isn't necessarily the one with the most parameters, but the one that learns most efficiently from its own environment. The best way to predict the future of AI is to build its self-improving core yourself. This is where your journey as an agent architect truly begins. I look forward to seeing the autonomous systems you'll deploy in the next chapter of our industry's evolution. In our next series, we'll dive even deeper into multi-agent orchestration. See you in the next build.